Bismillah ar-Rahman ar-Rahim. Hi, my name is Muhammad Jawad Zalaghi and I'm from Robotic Knowledge channel with you in Webots lecture series in our YouTube channel. In the previous lecture, I talked about how to create a word in Webots, how to put a turtle board in the created word, and how to give some motion command using velocity commands in Webots to a turtle board. In this lecture, I want to explain how we can use the gyro sensor in a turtle board to measure its rotational states. In some words, to measure its rotation angle. So please follow me and follow this lecture. This is going to be a fun lecture. This is our turtle board, and here is our controller that we have developed from the previous lecture. I'm going to create first a new controller. So for creating a new controller, I'm using file, a new, and new robot controller. I'm going to select Python programming language. The name is, for this lecture, my controller 1. I want to open this controller, so I'm using this controller, but I want to use what I developed in the previous lecture. So I'm going to the previous controller, Control A, Control C, then I will paste the developed code from the previous lecture, and I'm going to save this file. The first thing that we want to do in this lecture is to making this turtle board able to perform rotation in place. I mean pure rotation without any translational motion. For this purpose, we need to change our motion commands. The main reason behind this decision is that we want to verify the rotation angle which is measured using the gyro sensor, and we can verify and accept the measurements using our vision when we have performing pure rotation. So I'm going to these turn left and turn right functions. We need to have equal rotational speeds in the wheels, but in different directions. So I'm going to set the right wheel velocity speed over 2. When we want to turn left, actually the right wheel speed should be positive, so half of the speed with positive sign and half of the speed with negative sign for the left wheel. The same thing for the turn right, but with different signs, minus speed over 2 and here speed over 2. I want to be sure that our in-place rotation works, so I'm using this turn left command. Just let's see, pressing the simulation button. Before that, we need to reassign the controller. So I'm selecting this field, select, and here we are going to choose my controller 1. Okay, now I can save the project and run the simulation. you can see we are performing a rotation in place. I mean without changing the center of gravity of the turtle ball. One interesting thing here is that our there is a coordinate which is attached to the robot. This coordinate is called moving frame. So you can see the coordinate is moving. Actually it's not moving, it's under rotation. If I select the ground, you can see there is another coordinate which is called global coordinate, which is fixed because this coordinate is attached to the ground. Interesting thing here is that the rotation is happening about the z-axis of local frame, and fortunately the z-axis of the local coordinate is the same z-axis of the global coordinate, so we do not um, to transform the measurements of gyro in this specific direction. This make easier our work. So I want to test the rate, the turn right function. Also, I'm going to simulate my scenario again. You can see the angle of rotation is happening in a reverse mode. So we completed the first thing, in place rotation. The next thing I want to do is to consider how to set up the gyro. From the previous lecture, we can see our turtle bot here. I'm using its documentation in Cyberbotics documentation guide. Here is the address. You can see turtle bot has some rotational motors, has an accelerometer, has a compass, has a gyro actually, and has a LiDAR. So here I want just use gyro because the gyro measures the rotational rates of a platform in its local coordinate frame. For example, the rotational speed around x-axis, y-axis, and the z-axis. Again, in the Webots reference manual, here is its address. You can find the information about gyro. So interesting thing is here its description. They explain that gyro node is used to model 1, 2, and 3 axis angular velocity sensors, which is called actually gyroscope. Angular velocity is measured in radians per second. So gyro is returning angular rates. We can measure angular rate about z-axis of the robot, which is also the z-axis of the forward. We showed it in the in previous minutes. As a result, by performing some integration over that measurement, we can measure the change in the angle of rotation. This is a straightforward way. Also, I will show the theory behind this scenario, behind this story. Okay, I want to open Webots. The first thing is to define the gyro object. So I'm defining a variable which is called gyro. I'm using robot object, which is this turtle bot here. Again, here I'm using getDevice function. You are familiar with this function from our previous lecture, getDevice. What is the name of gyro sensor? We don't know. We have to use documentation. Here you can see the gyro name is gyro with lowercase g, so I'm just copy it. I'm returning to Webots and paste it here. We successfully defined our gyro object. You can see the code for wheel motors. When you are defining the wheel objects, you don't need to enable them or disable them, but when you are defining sensors, you have to at first enable that sensors. For enabling a sensor, type its name, gyro dot enable. Again, I'm going to simulate a robot. I want to see is it working or it's not working. You can see there is some error. It's saying that we enable okay one required positional argument p. We can see the documentation here. Yeah, nice point. So when you want to enable a sensor, you need to define the sampling period in which rate the measurements should happen actually. So I'm going back to Webots. From the previous lecture, we know the step time of the simulation is 32 milliseconds, which is stored in time step variable. So I'm going to use this time step variable as argument of this enable function. I'm going to save this update and performing the simulation again. You can see here without any error our controller is working, so we successfully enabled the gyro sensor. Okay, the next thing is getting the measurements of our gyro. For doing every work in Webots, you need to check its reference manual. I'm going to open the reference manual. You can see there is a function which is called get values. Using this function, you can read the measurements of a gyro. Get values. Copy. And I want to define a function for measuring the angular rates. I'm defining a function with name angular pulse and velocity. Angular pulse and velocity because we will show using integration we can find out the position, the rotational state of the robot around the z-axis. We know that omega x, omega y, and omega z are measured using this gyro. So gyro dot the function name get values. The measurements is happening in the local coordinate. Again, for giving explain here I have an error. We missed the argument. Again, we have the error. Okay. Just let me clear the console. Okay, the code is working now. I was talking about this. I'm going to talk about this again. Here is the robot. If I click on the robot, you can see there is a attached coordinate frame. What this gyro is measuring is around this moving frame, but more important for us is to measuring in the global coordinate, which is a stationary coordinate frame. At this point, due to the knowledge that this blue axis, this z axis, this global z axis is the same local axis, they are not, they are the same, and by this knowledge we are not going to complicate the problem. They are the same. What we are measuring in the local frame is the same that is viewed from the global frame. So let just print these values. These measurements which are happening in local frames are shown x, y, and z, which are not capital. Let me print here the omega z. You can see, because we are not calling this angular position velocity function, I need to call it in the loop. So there is nothing here. Here there is nothing. You can see we have a print function, but here there is nothing. The reason is there is some fault here. We are assigning an object, an array actually, to three scalar. It's not right. Actually, gyro.getValues is a vector. We need to use its components 0, and the first component is measurement in x direction, the second component is measurement in y direction, and the last component is the measurement around z axis. Okay, I'm going to save this function and running the simulation again. Here you can see the angular rate around z axis. It's constant, minus 1.16 or 17. It's obvious it's not the same thing, because it's not it's experimental, it's simulation of an experimental thing. The sensor has noise, the sensor is not measuring one thing in a perfect way, so it's obvious there are some small changes. Now I want to see that if the direction of movement is reversed, the sign of the measurement also is changing. So instead of turn right, I'm going to use turn left with the same amount of velocity. I'm going to run the simulation. Here you can see the results. So the minus value is returned with positive sign. So yeah, the sensor is working um, perfectly. The first thing that I want to explain is how to measure the rotational um, the rotational angle of this robot um, around the z-axis, because I talked and I'm saying it again. Uh, the z-axis of local coordinate and the z-axis of global coordinate are the same. So without any problem, we can use our measurement as a global measurement. Uh, I'm going to show you the theory behind this next implementation. So we know from the physics that the angular velocity is derivative of theta around z in respect to derivative of time. So we can say that differential of theta is equal to angular velocity times differential of time. So we can use integration from we can use integration of both sides from theta, the initial theta to the final theta, and the the right side, actually this is differential of time, not differential of theta, from initial time, which is 0, to the final time of t. The left side is theta minus theta o, and the right side is uh, in a discrete manner is summation of omega z times our simulation step for sample I from 0 to the case sample, which is our final simulation step. So this is the relation for um, making the measurement. The initial angle in our simulation is 0 because the coordinates are fit together, and the right side we are measuring this omega z, and we have the knowledge about delta t. This equation is true when delta t is small enough. In our simulation, delta t is 32 milliseconds, which is actually a tiny value, a tiny number. So I'm going back to my simulation. I'm going back to the angular position and velocity function. I don't want to measure, to print this um, angular velocity. I'm commenting this line of code. uh, I need to um, define the global variable for the theta around z-axis, theta around z. Its initial value is 0. It's outside of the functions, especially this angular position velocity function. I need to have access to this variable, so I'm using this syntax global to have access for change the value in this state, because theta z is going to change with time. Also I need to just let me make some here. Theta z is equal to um, previous theta z plus y previous theta z. This is actually implementation of the summation which we developed in the theory. We are summing every value with its previous state. So theta z is equal to theta z plus omega z times simulation times our time step here. Um, time step is integer number 32, but it's actually 32 milliseconds. So I'm going to consider that milliseconds unit here, 001. I'm interested in printing this measurement print theta z. So here is a global coordinate. I'm going to run the simulation. Okay, you can see it's increasing, and just verify the amount of, just let me verify this measurement. I'm going to stop simulation. Okay, so the simulation is here is just let me reduce the rotational speed. For example, with the wheel will rotate with 2 radian per second. With 1 radian per second, half of this value. I'm going to start the simulation. You can see here the robot rotates about half of the pi number around z axis. You can see the last step measurement is 1.57 90 degree, so the measurement is okay. I'm going to run the simulation again. Another pause here. It's about pi number, more than pi number. You can see some difference here, so it's okay. 3.17, and here the robot is in its initial position. You can see the measurement is 2 pi 6.27, which is near to 6.28. So what we are measuring is okay, and its evaluation is near to reality. I'm going to make some change here. When rotation is completed in one turn, I want to reset the value of the rotation because it's angle. So first I need to use pi number, import numpy as numpy in the function. I'm adding this logic if theta is greater or equal than 2 times numpy.pi. Reset the value of theta. So I'm going to run the simulation. You can see here the robot is rotating 4, 5, 6. The data is reset to 0. So we can measure the angle of rotation of this platform using gyro, and the final thing which I want to do is uh, plot of this angle. I'm interested in two plots. You can visualize, you can verify things using their plots. Um, to, 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 illustrate a plot here in Python, I'm using matplotlib. Import matplotlib dot pyplot as plt. In the loop, I need to have, because I want to plot a quantity with respect to time, um, so I need to define simulation time which is equal to 0. In each step of the loop, simulation type is equal to simulation time plus time step times 0, 0, 1. I want to make archive from my time steps, so time archive is equal to an empty array, not empty array. I want to add the initial value 0. Also, I want to create an archive for this angular um, measurement, angular position measurement, theta z underline archive is equal to, the initial value is 0, I know that. uh, Instead of going to print this state here, I'm going to add my measurement to my archive dot append theta z here. So I want to do this simulation for 10 seconds, so I'm going to add a logic here. If simulation time is greater or equal to 10, please break the loop, and outside the loop I'm going to plot my quantities. Actually, I want to plot the rotation angle of this turtle bot, so I'm using plt dot figure command to create a figure. Plt dot plot time archive should be plotted with theta around z axis archive, and finally I need to show what I have drawn. Okay, I think that works for me. Just let me clear the console. I'm going to running the simulation, so you can see the robot is rotating. Here consider the simulation time: 7, 8, 9, 10. Okay, we have some problems here. The loop is continuing, so Let's monitor this simulation time. Print simulation time. Yeah, that's great. 7, 8, 9, 10. Okay, now it's working. There are some error here. We have problem. Yeah, that's right. Okay, the time archive is not okay. There are some problems with time archive. We need to append um, our uh, instantaneous simulation time to this time archive. So simulation time dot actually dot append this simulation time. Just let me clear console, running the simulation again. Okay, there are some bugs here. App and right, append. So the controller is running. Here is the plot of time steps, a stream of time steps actually. Yeah, that's the measurement. You can see the final measurement here. uh, the you are rotating with constant velocity, so um, the angle is increasing linearly. That's right. I'm closing my figure. I need to increase this speed 6 radian per second for wheels, 3 actually radians per second for wheels. Again, running the simulation. It's interesting. Without the platform you can do these works. So you can see at the complete turn the um, the measurement is going to be resetted. It's obvious because um, we are in the origin when a complete turn is completed. So it's interesting. I think totally it's interesting. um, at this lecture we have learned how to set up the gyro sensor in a turtle board, how to use its measurements, and how to perform a simple numerical integrator in a function, and using that uh, we find the capability to measure the rotational angle of a turtle board. And all of the code is available here, the gyro definition and the angular position velocity around z-axis and implementation. Another interesting thing that we covered in this lecture was how to control the loop, the main loop of the Webots simulator, and how to break the loop, and outside the loop you can simply plot the results which help you to debug the developed controller for your robot. I hope you enjoyed the lecture and it was useful and helpful for you. Please follow our channel in YouTube and in our Telegram channel, which is both the The username of the both channels is robotic @robotic knowledge. And in the next step, I will try to use encoders, wheels encoders, to monitor the position of the center of gravity of this mobile robot platform turtle board. These are steps before using LiDAR, because um, we want to use LiDAR to monitor position of obstacles, and without the knowledge of the current position and current orientation of the robot, it's not possible to do that. um, I am Mohammad Jawad Zalaki from Robotic Knowledge channel. Please follow our channel and subscribe to our channel to be updated about this series of lectures in Webots. Thank you and bye bye.